So I want to go over a review of hydrostatic forces on plates. In thermofluids, you probably saw plates that are horizontal and vertical. So I want to review this and then add a little more of the curved surfaces that are so important because a lot of valves and gates can be curved. So we know that at a specific depth, the pressure does not change. So like in this case, you have the same fluid on top, and this is the pressure. The gauge pressure would be then raw GH. So whenever we're talking about the force is the pressure times the area. So here we have the area of a plate if it's A times B. So then we have the resultant force. And so this is the magnitude of the resultant force. We will use a two-dimensional approach, keeping in mind that it's a prism, really the pressure, but we'll always be using a two-dimensional approach like you did in statics. And what we'll look is at submerged plates that are vertical, and it can be a plate or it can be a wall. What's important to recognize is that the pressure, the hydrostatic pressure, which is due to water, even if the wall is very, very high, the hydrostatic pressure starts where the water starts. So this is 0, and you have a triangular, and this is like a line, P equals raw GH with intercept equals 0. So if you look at the form of this equation, M x plus b, so this is the slope. And this is your x, and then 0 intercept. So there's two questions. What is the magnitude of the resultant force and where it is located? Okay, so the pressure is raw GH, but how do I calculate the magnitude of the resultant force? That's an important question because here is all the pressure, not the average force. And this resultant force, what the magnitude and the location is two different things. So let's talk about the magnitude. The magnitude I calculate pressure at the centroid of the plate. Okay, in this case is the wall. So here I have my wall, and if I have this h distance, I will calculate the magnitude at h over 2. But the location of that resultant force is not there. The location, you have to look at the centroid of the distributed load. That's where the resultant force is located. So this goes back to your principles in statics. This is the triangular distributed load, and they said, well, where is the resultant force located? Well, it's located, in this case, let me delete this. And then this would be h. It would be 2/3 of h and 1/3 of h, because that is where the resultant force would be located. Okay, so the location of the center of pressure is this, and this is yp. Okay, and that is not the same as the centroid of the wall. You look at the centroid of the distributed pressure. Okay, so this is for a triangular. What is the magnitude? And then where is the centroid of the wall is a different story, right? And where the location of the center of pressure is different. So you calculate the resultant force at Here in this case, you have H, so it's going to be raw GH, centroid of the wall, and then from there I get my average force, which would be pressure times the area of the wall or the plate. The location then is at the centroid of the distributed load. So this is my resultant load, but the location. Okay. If you have a vertical submerged plate, it's just like the wall, but then remember, if you have water on both sides, then it's zero. Law of action reaction. So that's why whenever you're submerged in a car, I hope you never find yourself there, and the car is full of water, then there's no pressure. You can easily open the door. Okay? In your book, there's some surface area, centroid, and moment of inertia for simple geometric plates, and we'll see how those are used. And so the first case we saw was whenever the plate was submerged, but right at the surface, and now we have a distance s. If we had the initial case, then it would be like this, but as I mentioned, so now we have a plate submerged at a distance s, so that changes the profile of the pressure. So we have still the same notation, P, and then in this case we have a plate of height B. So the resultant force you calculate at the centroid of the plate. So when I look at the centroid of the plate, the pressure at the centroid of the plate would be S, or the pressure at S plus pressure at a distance, then I need to add S plus, well, I already put the S, so let me erase here, plus the pressure at B over 2. Okay? So the pressure would be, the gauge pressure would be raw G S plus V over 2, which would be here. So the force, the resultant force, would be that pressure divided by the area of the plate. Let's say that this is B and has a width A. The location of that force is different, the pressure point. So this is located in a different place, and that's what we'll see how you can calculate that. Okay, so the magnitude of the resultant force is equal to the product of the pressure at the centroid of the plate times the surface area of the plate. But the location is not the same. It's at the center of pressure, and that's what we'll need to calculate. What is that YP? Okay, so we'll call YC the location to the centroid of the plate, and YP the location of the center of pressure. Okay, so we have already calculated this, the resultant force at the centroid. And then for a rectangular plate, we have to, or for any plate, we have to look at the second moment of inertia. And if this is a rectangular plate, this is the second moment of inertia. You need to look at the equation that you're using, because in this case, here the width is A and the height is B. So it's A, B to the third. If you have it reversed, you need to keep an eye on that. So the location of the center of pressure would be the location of the centroid of the plate plus the second moment of inertia around the centroid divided by YC times A. So that's as easy as that. What you need to remember is that if you do your calculations and you get a YP lower than YC, it's not possible, because it's always YC plus something else. So in summary, this would be the hydrostatic force. You calculate the magnitude at the centroid of the plate. The location is YP, and this is the equation you use, and this is for vertical plates. This is an example from a previous book. It's important that you remember this is from thermofluids, so review those concepts. In the case of a horizontal plate, you don't need to calculate YP because this is the location of the centroid, and YP is the same because it's based on the depth. The pressure on inclined surfaces. So the concepts here are not going to change, but now you have to look at an angle. So we call now here HP and HC, and what was YP and YC is from the surface to the centroid and to the center of pressure, but it's at an angle. The pressure you don't calculate at this distance YP or YC. You don't use this YC. You use this because for hydrostatic pressure is based on vertical height. So HP, and this is your angle here, is YP times sine of zeta, and HC is YC times sine of theta. So that's what you need to keep in mind. But it's the same process. So now for a submerged tiled rectangular plate, so it's at an angle, the YP equals the YC, and of course you calculate this part here, so the height of the centroid based on, this is always half of the length, plus whatever distance you have. And now you have an angle, so you need to incorporate into your equation the expression for sine of theta. Okay, so it's important to recognize that. Now, for hydrostatic forces on curved surfaces, you have several options and several other additional steps. In the case of a curved surface, like you have here, let's say that this is your curved surface. There's two things, and I'll delete this for a moment. There's two forces. There's a vertical component, which is the weight of the water on top of this surface. And then, of course, there's the horizontal component from the pressure from the water on the side. So you have here this weight because it was cut into two pieces, and then this. So you have a vertical and a horizontal. So anytime you have a curved surface, you look at the water, at the weight of the water on top, on the vertical, that is your vertical component, and then the pressure on the side. And so the resultant force would be something, well, actually coming from this direction, that would be the resultant force, and it's following the same as in statics. So you have a horizontal and a vertical component, and then you have an angle, and then the resultant force. If you look at example 2.5 on page 28, it's very well explained. I don't think I can do a better job at explaining it. If you have questions, send me an email. But make sure that you practice that example, because also the homework problems will include some of these concepts. Thank you very much.